Thanks everybody for being here. It's a pleasure to talk about these, I would say, challenging topics these days. So I'm going to provide some background first, and then things that I have done with respect to using observations, particularly remote sensing ones, to characterize the water, carbon, and energy cycle themselves, and also the interactions, feedbacks, and couplings between these two. And I will show what is the motivation for these, where we are going, and why we need these, and what are the remaining challenges, which are actually many of them. So there are many processes that link these three cycles together, and that's causing the basically more challenge, because there's a lot of feedbacks and coupling in there, and they're like three gears that basically move together, and we need to have a better understanding of what's going on there. I would like to start with this famous figure from IPCC recent report. So we know we are emitting more anthropogenic CO2 into the atmosphere, the positive side of this figure. And the question is now, where is this CO2 going? So we have these three, I would say, reservoirs, which this CO2 is partitioning and going into three of them. The black kind of, or dark blue, is the kind of ocean sink. The ocean is absorbing a big chunk of those CO2, and it has been increasing over time, as we have observed, and also kind of simulated from ice records and kind of proxy measures we have. Then we have the light blue, which is the atmospheric concentration of CO2. That has also been increasing over time, but there has been ups and downs a lot. We see a lot of variability compared to the ocean, which is, I would say, more solidly increasing. And then we have the green side, which is the absorption by the ecosystem, or the terrestrial plants, basically. How they are reacting. There has been more CO2, so there's more gradient with respect to the what plants see in the CO2 in the atmosphere, so they do more photosynthesis, absorb more CO2, and they're acting as a sink, as we know. But there is a lot of variability here. So the variability which is actually caused in the atmosphere is because of how plants and the ecosystem is responding to the increased CO2. And this is a challenge. We don't know how plants are acting, why there is that much of variability, and what will happen in future. Will there still be a sink for the CO2, or at some point there might be a threshold that we don't see plants acting as a, I would say, increasing sink, and they will just die down because of increased tension. So I'm going to start why we are seeing these patterns. We want to study more on the plants. This is the famous figure from Brown's paper about 13 years ago on what is the constraint really under plant growth in different parts of the globe. And this is observation based. So yeah, we know from basic photosynthesis science that plants need water, appropriate temperature, nutrients, as well as radiation to do the photosynthesis. But what happens in different parts of the globe is that, okay, different parts have different types of constraints. For example, in the tropics, particularly the Amazon, is actually the radiation which is the limiting factor because of cloudiness in many days around the year. And water and temperature are actually perfect. In the Sahara, we don't have water that plants can grow. And at the same time, to some point, we have a little bit of high temperatures that can grow. And then in the kind of transitional zones, in the mid-latitudes, we have a mix of water and temperature. We have seasonality, we have sometimes dry seasons and also cold seasons. So plants are limited by that fact. But then it comes the question, okay, we know the constraints. How these plants are responding to those constraints, and what is the feedback between the surface and atmosphere? This is from one of our recent studies, which is now in revision. We are looking at what is the basically coupling between the biosphere and the atmosphere. So here we are using this SIF signal that I will explain much in detail in the later slides. This is the sun induced fluorescence. It's basically a remote sensing measure of how much fluorescence is emitted from the plants, which is a direct proxy of the GPP, or the plant photosynthesis activity. So here we are looking about the fraction of the variance explained in monthly data over 8 years of data of Precip to the SIF. So basically, in parts of the globe, we see up to 80% of the SIF is actually caused by Precip. And this is a causal measure, it's not just correlation. We are looking at the gradual causality in terms of the details of the methodology, and we are looking, okay, how much of the SIF can be explained by variability in precipitation, and how much of it can be explained by PAR, which is the photosynthetic active radiation. Basically, these are the three cycles. The Precip is the water cycle, SIF is the carbon cycle, and PAR is the energy cycle. We are looking how they are coupling. And what is the return? How much SIF impacts the Precip, or SIF impacts the PAR? And again, we see different patterns in different parts of the globe. So here, in all of these transitional zones, we see precipitation acting very highly. In this kind of boreal forest and higher mid-latitudes, we see power to be more important precip. And also in the Amazon, we don't see that much here. To the extent, we see a lot of power here, actually. So water, again, is not the limiting factor in the tropics. Also in the Congo Basin and in Indonesia. In parts like the Sahel and also the dry deserts of Australia, we don't see anything because of the significance of the test. So here, we only show the pixels that have a significance of p-value of 0.1 or so. So, from other literature, we also have looked at this coupling. And this is, again, the soil moisture temperature, so it's water cycle, energy cycle. We know if we have a change in soil moisture, we have change in evapotranspiration, and that impacts the temperature, and then loops back and feedbacks on the soil moisture itself. And this is kind of a positive feedback here. If we also incorporate precipitation here, we know increase in soil moisture, increases evapotranspiration. This link is still challenging, I will tell you how. We have increase in precipitation probably, and then we have increase in soil moisture. So that is again also a positive thing. And then there's also an inside coupling here between just evapotranspiration and soil moisture. Again, evapotranspiration is the kind of the main fluxes in the carbon cycle. So there's all three links here. And you see how soil moisture is acting as a kind of a boundary or a key storage here. Because these are fluxes, but soil moisture is a storage. So it really matters how soil moisture responds to these fluxes. Just to go back to this relationship with evapotranspiration and precipitation, some studies show actually increasing evapotranspiration increases precipitation, but some studies show the other way, because sometimes if you have actually dry soil, you have a more stable atmosphere for convection, and you have better kind of precipitation formation. So there is contradictory things here, and it really is the fact that we don't have a, I would say, solid relationship. In different parts, it might be different things. So it's not just one-way direction. And here also, the soil moisture precipitation is not always positive, because if you have a saturated soil and you have precipitation, you don't see increase there. But at the same time, you don't see decrease. So that's why we show this as a positive kind of couple. So soil moisture is really playing a role here. And now we have a satellite, a very good one NASA launched 3 years ago, SNAP, which is the soil moisture active-passive, name of the two instruments. And we are looking at how soil moisture is changing kind of on a daily basis. SNAP provides every 3 days, but now as of a couple of months ago, SNAP also provides afternoon measurements. So SNAP has kind of 6 a.m., 6 p.m. Equatorial time pass. So we have two sets of observations, but we have always been using the morning one because of the assumptions in the retrieval. Now they also provide soil moisture from the afternoon one. It is a little bit more uncertain, but it's not more than the kind of mission criteria. So they are providing that as a kind of official product. So far we have been getting 3-day measurement. Now we can get a day and a half, because we are almost have twice measurement as before. I'm still using the morning ones here, but that's what we are going from now on. And this is just a pattern of the average first year of SNAP over the Amazon, over the Africa, and you see the gradient over the Congo Basin to the Sahara. It has been a very good set of measurements here. Yeah.
So, is it really that important to have that frequent observations of soil moisture?
So, in terms of weather forecasting, yes. Yeah, maybe not in the climate studies, but in terms of more real-time operational things, yes, it's really needed, because, again, that's the initial condition for the atmospheric convection, what you see in the ground.
I see. And you think that these, let's say, every couple of days, they could make that much difference to the weather?
Yes, it does. I mean, so the next thing I'm showing, actually, it matters in terms of that frequency. So this is from the recent paper we had. So we know soil moisture is really small in terms of volume. It's less than 0.1000% of the water budget in terms of volume. But we know it has a lot of impacts from different studies on dust generation and how stream flow basically generates crop yield on some kind of biochemical cycles, how much water is available to the plant. So it has a key role, but it hasn't been characterized in that sense. So here we are looking at soil moisture in terms of that storage and memory, because it sits at a boundary that in the atmosphere we have kind of short-term anomalies. Let's say we have a thunderstorm, it's just 30 minutes. Then we have anomaly in the soil moisture, which might take days to weeks to go away. And then we have the basically subground or the underground water, which has time scales of months to years. So soil moisture is literally sitting at that boundary between these two time scales of the general water cycle. And we want to see how does it play a role, how much water really sits in that soil moisture. So this is the first year average of the soil moisture data from SMAP. Globally, we are just looking at the spatial patterns here, and this is the zonal average we have with the one standard deviation around it in the shaded regions. And the size of these dots is actually showing how much land we have in that latitude. So this is just the general knowledge. We expect to see these patterns, but now we are seeing it with the data, yes?
Yeah. How much depth SMAP is looking at?
So technically it's 5 centimeter, but in some regions can be less. So if you have more vegetation in the ground, you can see basically your signal has less penetration to the soil. And this happens particularly in the tropical regions. So SMAP, by definition, only has an error less than 0.04 cubic centimeter per cubic centimeter soil moisture for regions that vegetation water content is less than 5 kilogram per square meter.
Okay.
If it's more than that, it might have a good accuracy, but it's not guaranteed. Basically, it's not evaluated and it's not designed to see that.
Right.
So that's why in the next slide, in the tropical regions, I will put dots in there. That's a shaded region. The data might not be as accurate as we think, and might have, I mean, there's a still debate whether SMAP and other kind of microwaves are seeing the vegetation water content here or actually the soil moisture. So it's still, that's the challenge ongoing.
And what about if there is a rainfall in a, say, in the Amazon region, will that affect the signal that retrieval?
You mean clouds in general?
The clouds and rain?
No. Basically, the low frequency microwave penetrates through the clouds and water. I mean, that's why, for example, in GPM, which is also a microwave instrument, we also have higher frequencies. That goes, I mean, SMAP is 1.2 gigahertz, but GPM goes from like 18 to 100 gigahertz. So higher frequencies are more sensitive to what is in the atmosphere compared to the surface condition. And this is also the precipitation data for the same time period over the entire globe. And we are going to define this metric, which is called fractional stored precipitation. So if this is the surface layer of the soil, so for SMAP delta Z is 5 centimeter, we have a theta, which is the volumetric soil moisture, and we have inflow and outflow here from precipitation and ET, drainage, and runoff. We want to see after a frequency of F, which in this case is 1/3 because we have one observation per 3 days, how much of the precipitation is stored in soil moisture. So here we have two time series. You see two cases of the low fraction and high fraction. So here the black time series is just an hourly measurement from an in-situ measurement. This is just for comparison. And SMAP is seeing the red dots. So in this case, actually SMAP doesn't see this peak. So we don't see that kind of increase in the storage. But in this case, SMAP sees that increase, so we get that. But on average, over 1 year of data, we are hoping that a frequency of 1/3 will give us some good estimate of how much precipitation is stored in soil moisture. But yes, if we have a better, higher frequency observation, we get a different index. That's why the index is defined to be frequency dependent. And this is the result basically. So this is the fraction stored precipitation for frequency of 1/3 over the globe. And light blues are smaller values, and to the magenta we get the higher values. And these shaded regions are really noisy regions that we just excluded from the results because precipitation is so small. So this division that we had is really just noise. And these regions are the high vegetation water content. So because we are not sure how much soil moisture data we have is accurate there, we have just excluded them from the results. So what we see here is actually, again, in tropical regions, which we are not seeing here, we have a very small stored water fraction expected to some extent. Then in transitional and mid-latitude regions, we get much higher values, and you see the peak of the basically latitudinal average here. And then as we go again upper, we get smaller values in the stored fraction of precipitation. And on average globally, we see 14% of precipitation remains in soil moisture after 3 days. That is a significant number compared to the 1,000% by volume of water budget that we see in the soil moisture. Yes, it's a very small volume in terms of storage, but really 14% of water is still in soil moisture after after 3 days. And that's a significant number because this really provides an insight, okay, what's the coupling between this soil moisture and the weather after 3 days? What's happening there? This is what we need going forward. This was just a, I would say, quantitative measure of that memory that soil moisture is playing here. And we have looked at this in dynamic terms and also in terms of static values over 1 year. Yes?
What is the internal color mapping for the
So,
soil?
I was going to say that this is the average soil moisture. So the drier regions actually have higher fraction of the stored precipitation, and the wetter regions, so the blue regions, the blues are more soil moisture, and yellows are low soil moisture, and these are the basically mean values. And we have actually a figure on that. So this is soil moisture, average soil moisture here, and this is the fractional stored precipitation. As expected, this is more of a check. The higher the soil moisture value, smaller the memory or the stored fractional precipitation. So this is again another kind of characterization of what soil moisture plays a role here. So from this one going forward, I want to show you, okay, we have now SMAP, it sees the surface soil moisture. We have good characterization. SMAP had two instruments. The name comes from active passive, a radar and a radiometer, but unfortunately the radar failed after 2.5 months of operation, so we don't have the active measurement. But what is next is, okay, how can we measure now roots on soil moisture? What is the technology there? What can we do there? That's what the AirMOS mission came. So AirMOS was an airborne mission called Airborne Microwave Observatory of Subcanopy and Subsurface. So it's a lower frequency compared to SMAP. So this is around 400 megahertz. It's in P-band frequency. So it has more penetration to the soil, so it can see, depending on the soil texture and soil moisture, up to 50 centimeters of the soil. That's why we call it a roots on soil moisture monitoring. It had campaigns over different biomes in North America for 3 years. This was an airborne mission finished. I mean, the last flight was in September 2015, but still data and processing are ongoing. And now I'm going to show, okay, how can we use the P-band now to get a better understanding of the roots on soil moisture? So if this works and we get a good, I would say, confidence in the retrieval algorithms, in future we might have a satellite with P-band. So what I worked on here was the first step in using this AirMOS data, and that is, okay, we have this active signal. So this is a SAR instrument, synthetic aperture radar. So it sends a signal, it gets a backscatter from the surface, as here, and we have interactions from the surface backscatter which comes to the sensor, a double bounce or dihedral between the surface and vegetation, so it keeps and it actually brings to us information from both the surface and vegetation, and signal that just backscatters directly from the vegetation. So it's actually more challenging compared to the radiometer because you have all of these interactions. And this is the kind of difference between active and passive. So what I worked on in AirMOS was, okay, how can we separate these contributions? We don't want to retrieve the parameters yet. We just want to separate how much contribution is coming from surface, how much dihedral, how much volume. And doing this in a sense that we don't know anything about vegetation. Because part of the AirMOS mission was to going into the field, taking samples from the vegetation, and then developing a vegetation model to do the retrieval. But if you want to have a satellite, then that's not, I would say, doable. We can't monitor all of the vegetation across the globe. So let's do something, come up with a more generalized framework and see if it works. So that's what I did using what we call polarimetric measurements to do this retrieval. I won't go to the details, I want to show you the results that we had. So this is kind of an agricultural system in Walnut Gulch in Arizona, which we have these pivotal systems and bare land around it. The Google Earth image is not from the same time that the measurement is made, but just give you an idea of what's going on the surface. And here I'm showing the ratio of the surface contribution to the total power, the double bounce, the vegetation, and this is what we call an Rgb decomposition. Basically, we put these 3 layers at 3 colors. Basically, red is the double bounce, green is vegetation, which is untreated, and blue is the surface. So when you see green, you have more vegetation. When you see blue, you get more contribution from surface, and red, you get more from the double bounce. So this is looking, okay, does it work really well? So we clearly separate these pivotal systems. When we have this agriculture of these active and vegetation ongoing, we get less contribution from the surface. And here we are just using a very simple, I would say, vegetation model. There's no parameter there. But still, we are fitting all of the fields very well. There are issues there, of course, these two that I am crossing here. We don't know what's happening there because particularly we don't get that much vegetation contribution, but we get a lot of double bounce. Which is a little counterintuitive because double bounce was between surface and vegetation. If there's no vegetation, how we are getting that? But it might be just the structure is different. We are investigating this and reporting in the paper. Maybe it's the earliest stages of the vegetation. It doesn't have that much leaves to basically have that, I would say, direct backscattering, but the trunks have this contribution for the double bounce. So this is ongoing and kind of a step for algorithm retrieval for future efforts.
Can you identify those in the high-res?
These are these two. But again, because the image is not from the same time, it's really hard to say what's going on there. And really went to all of the Google circle imagery, couldn't find this, what's happening
Did
there.
someone put a pile of mud on?
It might be, but this pattern you see here, this kind of crust, this shows that something is happening really with vegetation, because some of these pivotal systems are not full circle. And this is what's happening here, actually.
Yes, yeah.
This is not also full. So it's definitely something with the agriculture, but it's really interesting to see there. And something interesting shows up here is this pivotal systems itself that shows up as direct kind of cross-pole, so it comes to the vegetation.
Is it possible they were being watered at that moment?
It can be, but again, if it's water, we should also get higher surface contribution. Yeah, it's all of these scenarios can work. It might be just a different surface roughness, because really the surface roughness here plays a role in how much contribution we get back. But yeah, all of these scenarios are questions that we are asking. This is really fine resolution data, around 100 meters, so it's a lot of variability going on there. We are also using this data to see how much seasonal patterns we see. So this is data from the same Airmoss mission at Tonzi Ranch, which is north of here. From an in-situ measurement, we know in two different campaigns in wet and dry season, February and September, we see a distinct pattern between the soil moisture in depth. So this is the profile of soil moisture, this is the value of soil moisture, blue is for wet season in February, and this is in September for dry. And here we are looking at 3 different days of measurement in wet season and dry season. What is the PDF of the surface contribution, vegetation contribution, and the hydro contribution? And if you look at these two, the surface contribution in dry season is actually higher. You might expect, okay, I have low soil moisture, how I'm getting more contribution from the surface? But that's actually the counterintuitive fact here. This is relative contribution. Because we have a dry season, lower vegetation contribution, so we are getting more power in terms of basically ratios, not the absolute values, from the surface. So again, these are facts that are coming up and will help, okay, should I in future focus on the dihedral to surface to retrieve the surface condition, or should I focus on the surface to retrieve the surface condition? Because we can get the soil moisture from the double bounce, because it was contribution from surface and vegetation. So these are insights how we can do this in future. And now, the next step, this is another study, this is, okay, how can we use L-band and P-band together? This is kind of the new calls in the National Decadal Survey now, that let's use P-band and L-band together in a joint mission, so we have more observation and more constraint and retrieval of the surface condition and vegetation contribution. Because currently, for example, in SMAP, we are assuming the vegetation, where we see the water content, is something from the seasonal value. And then the temperature of the vegetation is the same as the surface. We are making these assumptions about the vegetation kind of condition, and then retrieving soil moisture. So somehow our retrieval is diluted with the assumptions we are making about vegetation. But here I'm looking, this was by chance, we had the same observation of L-band and P-band in one campaign in Oklahoma. So Airmoss was doing campaign, we had P-band data, and UAVSAR from the L-band mission was also doing a campaign. This was actually in 2012. And they had kind of 3-hour difference, but there was no precipitation in between, so a little bit of assumption there. But now we're looking, okay, how much surface contribution from P-band we get, how much from L-band we get. The resolution is different because the frequencies are different and they were not designed to have the same structure. But we are looking, okay, this is the same kind of color scale, and we see much more red in the P-band compared to the L-band. And we're looking, okay, what patterns do we miss in L-band or in P-band? For example, this is structure here that shows up in L-band, we don't see in P-band. What's going on there, for example? Is it surface roughness, for example? And sometimes we see actually tillage from the agricultural activity showing up in the decomposition pattern. So these are things that would really matter. And the conclusion we get from here is that actually surface roughness, which in many of the algorithm developments is just assumed to be constant value, is much more important than many other variables. So we actually need both observations to be able to retrieve surface roughness as well. So this is what's actually going on in future, and this is the basically histogram of the contribution over this domain, and again we see the mode and mean of the p-band being much higher than the L-band. So we get more penetration and more contribution as we expect, but how can we use it in future? That's what we are discussing in the paper and basically looking at the new retrieval algorithm development. But now going back, this was up to the point that, okay, we have this soil moisture acting as the, I would say, storage in that linkage of the water, carbon, and energy cycle. But what about the fluxes? There are a lot of fluxes going on from the surface to the atmosphere. And these are what we call the turbulent fluxes. The sensible heat flux, the latent heat flux, and the gross primary productivity. These are three of the main ones. We have also the MPP, which comes in later, but we don't have it in this study yet. And we also know that, again, soil moisture plays a key role between the partitioning of these two surface fluxes. So we want to see if we can use remote sensing data again, and also estimate these three fluxes at a global scale. Because all of these, again, are key to how the ecosystem and biosphere are responding to the changes, and if we can estimate these three much better, we can have a better constraint on these three cycles. So here, we are going to use that sun-induced fluorescence that I mentioned. So SIF, or sun-induced fluorescence, is basically a signal which is emitted by plants as part of the photosynthetic activity. It's a very small percentage of the total absorbed radiation, but it's like 1 to 2%, but it still is now detectable by the satellites. So that energy which is absorbed by the plant partially goes to the main thing, which is the photosynthesis, or GPP. Part of it is lost as heat, and a small fraction comes as SIF. And this is just from lab studies that they have leaf in sun and in shade, and they look at the different frequencies. And we know that at these two frequencies, it's actually now to be 683 based on new modelings, and 740, these are the two peaks of the fluorescence. These are nanometer, 680 nanometer and 740 nanometer. And we see more activity from the leaf, which is in the sun, compared to the one in the shade. So these are field scale studies that has been ongoing. But about 5 years ago, people at NASA Goddard and Caltech noticed that actually from one of the ongoing missions, which was the METEP-A satellite from ESA, and also the GOSAT mission from the Japanese agency, they can retrieve SIF. I mean, the instrument has enough spectral resolution because this is a very fine kind of signal, and they can retrieve that. So they started generating the product, and it came to be very useful. And one of the studies, people compared the SIF to the GPP estimates across different crops in different parts, and they see a very distinct linear relationship between the SIF and GPP. So at larger scales and at different crops, you see these linear relationships. Yes, the slope is different between different products, but in general, the more GPP you have, the more SIF you get. So, and also different other studies that I will show also show that SIF is more sensitive to the photosynthesis because it's the direct kind of byproduct of photosynthesis. It's a real-time measurement compared to like NDVI or EVI, which are a little delayed after the photosynthesis either picks up or goes down. So here we are going to use this SIF to be able to retrieve those fluxes. This is a kind of comparison how SIF and EVI compare to the seasonality of data. So this is 4 different regions in the tropics. This is wet Amazon. The blue is the monthly average of precipitation. The red is the radiation. Black is EVI, and green is SIF. And we are looking how particularly SIF and EVI have difference in different regions. We know in wet Amazon that photosynthesis actually picks up after the wet season, and that's because of the radiation limitation from the earlier pictures, if you remember I showed you. And this is very well captured by the SIF actually. When precipitation goes down, SIF goes up together with the radiation. But EVI is almost constant actually. To some extent, NDVI has the same pattern there. Here in dry Amazon, both EVI and SIF respond to this dryness after the precipitation goes down. To some extent, I would say both have similar patterns. Maybe SIF is more sharp, but that is relatively speaking. The other interesting one is in Congo, that we know has actually 2 wet seasons because of the type of weather and climate system there. And this is captured by the precipitation and also SIF. But again, NDVI seems to be, and EVI seems to be kind of a flat thing. So this is how SIF can be better than the kind of regular optical indices we have so far. Doesn't mean those are not useful. In many regions, actually, they are much better than SIF. This is particularly in the tropics that we are showing this. And in Indonesia, actually, there is not that much seasonality, and neither of the signals capture any seasonality there. So here, for the retrieval, we are going to use actually a statistical model. Maybe the first thing that comes to mind, okay, why not a radiative transfer model with a land surface? Let's do that and plug this very great observation, do that. But there's also uncertainties in using that model, because it's a physical model. We have understanding of the processes there, but maybe we are not complete there. And also there will be a lot of uncertainty on the parameters of that model that we are using. So instead of that, we are going to use a statistical neural network model. That doesn't mean we should not use this. No, it means just it's a different approach. We're going to compare the results and see what's going on. I mean, always when I show this slide, I say this famous quote from Sam Callan, the famous mathematician from Stanford, that the purpose of these models is not to answer the questions. We want to sharpen the questions. So we are going to have better models, more models to compare them and get a better understanding of what's going on with the processes that we are studying. And this retrieval is actually called WeCan. It resembles Yes We Can. And it's water, energy, and carbon with artificial neural networks. So we are studying these three cycles using the neural network thing. But what is neural network? It's basically a statistical retrieval. We have inputs, which in this case are remote sensing. We have some output, which initially should provide some target or scene observation. And then we feed this statistical model in between. But the first challenge that comes to mind, okay, what should be the training data set? How should I define a good training data set? So that is a challenge and will still remain a challenge in earth science. What is really the truth? We don't know. We have different measurement systems. We have models that see something. We have satellites. We have in-situ data. And these different instruments are looking at different scales, and they have different, I would say, representativeness. And here comes the challenge. Okay, how can I use these different measurements and define a good truth? One of the ways that we can do that, and it's a kind of a recent development, is a method called triple collocation. And that means if I have three measurements of the same variable collocated, let's say I have soil moisture and I have satellite, I have a reanalysis data from a model, and I have in-situ data. I can use those three measurements to characterize the variance of the random error without assuming each of them to be the truth. So only thing that is assumed is that this measurement has a relationship with the truth, and now I'm characterizing the RMSE of the random error in those measurements. Well, how that can be useful here? We use this triple collocation with three different flux measurements. We have LE, H, and GPP. So we brought in three LE measurements. We characterize the variance of random error in each node, which is this sigma of epsilon I for each of the i's, which are three here. And then we define a prior probability for each of those basically measurement system. We said, okay, I'm showing the names here, it's much better. Let's say for LE, I have the gleam, I have the ECMWF model, and I have the flux at MT. I give a weight to each of these three in each pixel based on the historical error I define. And then I sample from each of these based on the probabilities I given to them and generate a new target data set, which is a merged product of those three. So the one that has higher error, we get a lower weight and it will sample less, and the one which has a lower error will be sampled more. So I will have a target data set which is generated from the information content of those three, and I will train the neural network on that. And that showed to be actually very promising. And at the end, when we do the comparison, we are beating each of those three training products. So the triple collocation actually works very well here. So these are the training data sets we use, and these are the inputs to the network. So we have the SIF, net radiation, the surface air temperature, soil moisture, precipitation, and a snow water equivalent. How we come up with this list? It was initially basically knowledge. We know how these cycles react, what are the key variables there, and then we did significance tests if really, for example, precipitation plays a role in that retrieval. If soil moisture plays a role, how does SIF plays a role? These are the things that we did. And the retrievals are at monthly time scale, and this is because of the limitation in the precipitation and the SIF retrieval. And 1 degree by 1 degree spatial resolution, currently available from 2007 to the end of 2015. We can't go back in time because we don't have SIF before that, but we'll move forward soon with the new kind of retrievals. So here I'm showing the result. This is actually the results of the triple collocation. So this column is for the latent heat, and we are showing the error of each of these products retrieved from the basically triple collocation algorithm. One of the, to some extent nice, but also unfortunate things comes up. We know the fluxed MT, which is basically the upscale version of the FluxNet data. Because of few flux towers in India, for example, it's very uncertain there. And we see higher errors in fluxed MT compared to these other products. This is an example, many people talk about that.
But that's not unique to India, though.
Yeah. No, I mean, it's just an example, because many of the papers talk about this. That's why I'm referring to this, because this is a very known region in the fluxed MT, that people say, okay, here we have an issue, because it's a very active kind of region. We have monsoons, we need a lot of data there, but we don't have, so it comes up in many of the studies. Then we have the sensible heat, and actually we get higher errors in the central regions of the tropics because of the kind of modeling system and issues we have there. Actually, GPPs here, GPPs also is the same in the tropics, particularly in the LVF and the MODIS. This is the remote sensing one, but actually the fluxed MT is doing a good job in the tropics. And this is again all of the patterns we have there. So we use this, we define the weights and the target data set, and this is the retrieval. So this is the annual latent heat, this is the annual H, annual GPP. The special patterns, again, we expect to see these, and it works well. Then we did comparison. This is now all of the retrievals we have compared to the data, the target data that we generated. We want to see how good our training is working. And just to mention, the training was on the first 2 years of the data, and this is from the validation, which is the year after. So we want to make sure that the network is not overfitted, as they call it in the neural network. We don't want to just fit to the target data that we gave to the model. We want to have basically general model that works with all of the conditions. We get very good R-squared and RMSDs. This is the animation of the data, starting with the January 2007. I call this Earth breathing. It's just going up and down in the seasons. We see very sharp patterns. In the Sahel, we see the very good kind of seasonality capture. Tropics doing very good. If it comes to the summer, you see corn belts in the US capturing both of the GPP and latent heat, and the sensible heat also doing a very good job, again, in the Sahel region, the West US, and also Australia, how the basically wet part is different than the desert part in the kind of fall and spring. These are, again, snapshots of the seasonal pattern there, things that I just show you, the kind of corn belt in the Sahel. This is the edge, again, seasonal patterns. Let me move to the validation. So there is always this challenge, okay, how we want to validate the retrievals. The typical thing in the flux community is to compare with the FluxNet. So we did this, but very cautiously, because our retrievals are 1 degree by 1 degree, and those flux towers are just a point measurement. Some of them have a, I would say, good representative area, but some of them don't. For example, this one is in Finland. So the black one in all of the 3 figures are observations. This is latent heat, sensible heat, and GPP. And the magenta is our weekend, and the other 3 are the 3 products that we use for training. And generally, I would say 90% of the towers, we are doing a better job in capturing the seasonality and the interannual variability. That is also a challenge. For example, FluxNet is known to not have an interannual variability will capture. So that's actually the focus here. Are we capturing those things very well or not? And this is just a visual comparison, but we also did kind of statistical comparison with different indices, and we are showing that in the paper that it's actually much better than those 3. So we are learning from those 3 uncertain measurements collectively and doing a better job than those 3 by having that kind of initial condition of the errors. But we also have bad ones. This is the one in Belgium, and we see actually none of the 3 is very well capturing the seasonality. The peaks are a little shifted. But this was a little, I would say, uncertain in terms of the observation themselves, because if you compare the sensible heat to latent heat, for example, let's say this year and this year, you see almost twice the value of the latent heat showing up in the sensible heat, which is a bit weird in some region like Belgium. So there might be issues with the observation. So we are not saying we are better or they are better, we are just discussing this in the paper, that okay, maybe something is wrong with the observations. Those are also observations and they have their own uncertainty and error. So these are the type of things that we discussed there. But in general, a very good product. Some of colleagues are now using this to assimilate them in some models and see how it goes. Some people are using for validation, and we have been really, I would say, fortunate with the feedback we got from the community. So, getting to the conclusion. So, I started with the fact that, okay, we don't know how the biosphere is acting or responding to the increasing CO2. This is still the remaining challenge. What we need there is that because of these interconnection of these three cycles, we need to have better understanding of these feedbacks, and that needs basically more modeling and more use of the observational data to characterize those errors. I talked about soil moisture, how being a very small fraction of the water budget, but at the same time playing a key role in the global weather cycle as we call it. And then also what happens with the future observations of the soil moisture with the new instruments and the P-band, so we can get the root zone soil moisture. And also how SIF can be used as a better proxy for the vegetation photosynthesis activity and the new kind of weekend product that we have. Besides that, I will show one slide of what I'm doing right now. These are the things that were done. So we are now working on a new neural network for root zone soil moisture. And the logic here is that, okay, we have SMAP, which sees the surface condition. If you want to get the root zone soil moisture, we know that is very much interlinked with the plant activity and the plant water potential, the leaf water potential. So we are using another instrument, which is the AMSER2 instrument. AMSER2 has a much higher frequency, it's in X-band, which is around 10 gigahertz. So it doesn't actually penetrate through the canopy. It sees the top of the vegetation. And it has some information about the leaf water potential. And because it's a nighttime measurement, so we are making the assumption, okay, at nighttime we don't have any photosynthesis. I mean, we have much less, in some cases we have a little bit. And so the leaf water potential is in hydraulic balance with the soil matrix. So we can get some information from the soil moisture in the root zone from that top of vegetation observation. This is the very first results of that this is the target data set, this is the kind of retrieved soil moisture. These are root zone soil moisture as we define. Doing good, but it still needs some, I would say, fine tuning. So this is ongoing, and again, a neural network kind of retrieval there. And thanks for your attention, and also all of the colleagues and institutions that have provided support over the years for these things. Thank you.